Now we're going to apply all of our transformations unit to our exponentials unit. So the very first thing you have to be able to determine is what exponential function is your parent function. So you have to look for the base of the function. And then we are going to do the same thing we've always done. Notice this equation here. If above it you want to write it with the k on the other side. All we're going to do is do our transformations from left to right, just like we always have. If you find that this is a lot easier to memorize than moving from left to right, maybe it sounds, it's easy to pronounce, x de psych. If that works for you, then go with that. But you'll have to remember what all your letters were to begin with. In my opinion, it's going to be easier just to work from left to right. So right beside this question, in the space beside and the space below, we're going to do an example. So we're going to graph y equals negative 5 times 3 to the 2x plus 4 minus 7. That would be the equation. The green boxes wouldn't be there when you got the equation, but the green boxes are there for you to recognize that my parent function, the one that it's related to, is y equals 3 to the x. So the very first thing is off to the side, you're going to y equals 3 to the x. Draw a quick little sketch of that graph. You know the points on that graph are at 0, 1, and 1, 3, and that it has an asymptote at y equals 0. So when we do our transformations, we're going to take these 3 points, or sorry, these 2 points and the asymptote. So we're going to say, well, what's going to happen to 0, 1? What's going to happen to 1, 3? And what's going to happen to our asymptote of y equals 0? So in the same way that we've done this before, we move from left to right. We do our transformations one thing at a time. Well, sort of one thing at a time. We'll do all of our stretches and compressions first. So the negative 5 means that you're going to multiply your y value by a negative 5. That's going to be a reflection over the x-axis and a vertical stretch by a factor of 5. And with the 2 inside, so sort of recognize that all of this underlined in red is inside where the x was. So all of that underlined in red is all going to be horizontal stuff. That x of 2, that's going to take your x coordinate and multiply it by half. So our y coordinate is getting multiplied by negative 5, our x coordinate by half. How does that affect these 2 points? Well, this one's going to become 0, negative 5, and this one is going to become 1/2 negative 15. Continuing to go left to right, we hit the 4 and we hit the negative 7. Those are both vertical and horizontal translations. The plus 4 means x goes 4 to the left. And the minus 7 means that y goes 5 down. So now what happens when I go 4 to the left? I'm going to get negative 4, 5 down, negative 10. When I go 4 to the left, I'm going to get negative 3.5, 5 down. Sorry, 7 down. Yeah. I don't know where I got a 5 from. There, 7. Negative 12. Look at this. Oh, great save. And 7 down here, negative 22. Now that we've done the points, let's think about the asymptote. If you went across and you have y equals 0, first of all, can you notice that the only thing that's going to affect a y equals 0 is stuff that happens to the y? And so multiplying y equals 0, x by half doesn't make a difference. But all of the things with y are going to make a difference. But since it's 0 to begin with, multiplying y by anything is not going to make any difference whatsoever, since it's already 0. The only thing that's going to affect a horizontal asymptote is if you shift it up or down. Shifting it left and right will keep it exactly where it is. Multiplying it, since it started at 0, is going to keep it at 0. So the only thing that's going to affect it is the fact that you're moving it 7 down. So our new asymptote is going to be at y equals -7. Now that we have all of this information, we're going to plot our two new points and draw our new asymptote, and then draw our exponential function. So at -7, just create a place where -7 is going to be. That's going to be my asymptote. My points, I'm going to have 4, -12. 1, 2, 3, 4, -4, sorry. -4, -12. Label that. -3.5, -22. Estimate about where that would be. Now, if these are my 2 points and I need to have an exponential function curving through them, this is the only graph that makes sense. Now, one of the things that I always do after I've done my points and got my new graph is I sort of take my original graph and just run through all of my transformations one at a time. So, if I'm going from left to right, what does the negative do? I'm doing it one at a time. The negative's going to flip it down. So that would look like this. Then the 5 would stretch it vertically. So now it would look like that. After the 5, I've got a 2, which would compress it by a half. So now my graph looks like this. The +4 is going to move it 4 to the left, or click to the next screen. There we go. 4 to the left would look like that. And finally, the -7 would move it 7 down. Does that match up with our graph in the end? Generally. Now, I wouldn't draw all those things out. I'd sort of visualize each one in my head and say, does that match with my final graph? More or less. Is the shape right? Yes. And so we know that this is going to be the graph of this with all of those transformations. So everything we have from our transformations unit now applies to this unit. What makes it harder or different is how many parent graphs are there for exponentials. There's an infinite amount. So you first have to find out what is my parent graph, and then after that, use those points to do all your transformations. Because we could have a 6 to the x, or a 7 to the x, or a negative, well, not a negative, because that would come out in front. But you can have a ton of different values in there. So here is our first example. We want to use the graph of y equals 2 to the x. Normally, they wouldn't even tell you this part. You would look at this equation, and you'd have to recognize that y equals 2 to the x is your parent graph. And you want to sketch the graph of y equals 2 to the -x plus 2. So just like we did before, the first thing you're going to do off to the side is draw a quick sketch of 2 to the x with your asymptote at y equals 0. You know that it has the point 0, 1, and 1, 2. And you want to graph y equals 2 to the -x plus 2. So sometimes what I do in these equations is I take out a highlighter or just a pen like I did with the squares last time. I highlight my x, I highlight my 2, to remind myself that those are not part of my transformations. When I'm going from left to right, I'm going to hit a 3, a negative, and a 2. This 2 is not a transformation. That's part of your parent graph, because that 2 is right here and that x is right there. So now let's just describe things before we actually do the transformations. What's the 3 going to do? Vertical or horizontal? Vertical. Stretch or compression? Stretch. What about the negative? That's a reflection, right? Is that a reflection over the y, or is it a reflection over the x? It's a reflection over the y. Again, part of the way that I remember my negatives is I say, okay, the negative is where my x is. If I take a point and I make the x coordinate negative, it flips it over the y-axis. Take the point 1, 5. You make the x coordinate negative, you have negative 1, 5. Your x coordinate's changing, and if your x coordinate changes, it moves it horizontally. That'll be a reflection over the y-axis. What about the 2? Horizontal or vertical? Horizontal, because it's in the exponent where the x is. And is it going to move it to the left or to the right? To the left. And that's our gut feeling, right? Because we see the +2. But remember the special note that we had in transformations. Whenever you have a horizontal stretch or a horizontal reflection and a horizontal translation, you have to write it in the factored form. Notice the example that we just completed. If I go back up to it, notice that my 2 here was factored out and I had extra brackets. So then it was a translation of 4 to the left. In our example right here, that negative isn't factored out. So we have to take an extra step in this one. And write this as a negative bracket x minus 2. And it's actually going to be a translation 2 to the right. Now that we've got our equation set up properly to move from left to right, we can take our 2 points, 0, 1, 1, 2. We can write down our asymptote for later, and we can do our transformations. First of all, the y is going to get multiplied by 3. The x is going to get multiplied by a negative 1. What's going to happen to our first points? Well, we're going to have 0, 3 and negative 1, 6. Then the only number that we have left when we're moving from left to right is that -2. That -2 is going to shift everything 2 to the right. So we have 2, 3 and 1, 6. What's going to happen to our asymptote? Again, the only thing that's going to affect that asymptote at y = 0 is if you shift it up or down. We're not shifting up or down at all, so our asymptote stays at y = 0. So our final graph, I always like to start by putting the asymptote in, y = 0. Then plug in your 2 points. So I have the point 1, 6. If I left that 1, 6 just as a dot with ticky marks like I've done here, you're going to lose a half a mark for scale. You have to indicate some way what your marks on your axes mean. So as soon as I label 1, 6, I'm telling everybody that every mark vertically is going by 1, every mark horizontally is going by 1, and you're fine. I could also have done that just by putting a 6 here and a 1 there. Then it's obvious that that point is 1, 6. I would highly recommend labeling all of your points. So we have 1, 6, label it, 2, 3, label it, and you'll be fine. Which way is this graph going to go? Well, given that I have these 2 points, this is the only way that I can draw my exponential curve, and there's my final graph. So for part B, they asked some characteristic stuff here. Is this one increasing or decreasing as we go from left to right? It's decreasing. What about the intercepts? Well, since there's an asymptote at y = 0, there's no x-intercepts. If I wanted to find the y-intercept, how do I do that? Plug in 0 for x. So if I plug in 0 for x, I'm going to get 2 to the power of 2, which is 4, times that 3 out in front, which is 12. So apparently, it doesn't show up on my graph, but apparently my graph will cross the x-axis, or sorry, the y-axis at 12. The equation of the asymptote, y equals 0. The domain of the function, well, domain of all exponential functions is always going to be everything. The range of your function is going to be dependent on where that asymptote is. Since our asymptote is at 0 and it's above 0, we'd write it as y is greater than 0. Question from your homework for this one is number 10. But before we do that, we are going to add 2 more examples. And I'm going to get you to add those examples on page, I believe 357 is a blank page. Is that right? In our function on exponential units and logarithms, which we haven't done the logarithms yet, there is a very important number that maybe you've never heard of before. Have you heard of the number e? Okay, most people think it's a letter, but it's a number as well. Do you know the decimal places of e, what it's approximately? E is like a number like pi. Pi is 3.1415. How many decimal places do you know? Keeps on going forever. E is a number like that too. However, when you memorize pi, you memorize 3.14 like in grade 8, and you never spent any time really learning the other decimal places after that. Probably you don't know too many after that. E is easier to memorize than pi for the first like 9 decimal places. It's 2.718281828, and that's kind of nice, but it doesn't keep going like that. Then after that, it goes crazy in a bunch of different numbers. But this is approximately what e is. So in our exponential function, e is a very important exponential function. It becomes up even more important as we get into calculus. So we need to know how to graph functions with a base of e. And it's not harder than functions with a base of 2 or a base of 3. It's just different. Because you're still going to have an asymptote at y equals 0. You're still going to have the point 0, 1. And you're now going to have the point 1, e. Will that 1, e cause this graph to be increasing or decreasing? Increasing, because e is 2.7-ish. So that's above 1. So here's the graph of e to the x. Like I said, it has exactly the same shape as 3 to the x, 4 to the x, 2 to the x, 5 to the x. It's just got a base that is, depending on how you look at it, either a beautiful number, because it's important, or an ugly number because it's a decimal that continues on forever. But this is the graph of y equals e to the x. Yes? Well, it's an important number because it's the only number, if you take the derivative of this function when you get to calculus, that its derivative is itself. So you have no idea what that means yet. But if I take this point right here and I draw a tangent line at that point, okay? Remember tangents from tangents to circles, a point that touches the graph only once. The slope of this line happens to be e, which is the same as the y value. And if you went to 2, e squared, and you drew a tangent at that point, the slope of that tangent happens to be e squared. And it's the only function who has that property. No matter where you draw a tangent, this tangent at 0, 1 has a slope of 1. It's the only place where that comes up. Now that is one aspect of where E is important in calculus. But there are other things where E comes up important, especially in modeling population growth or in continuous growth of any matter. So in other words, our bacteria at the beginning was shown to double every so many hours, okay? And when bacteria is large enough that it's always growing, we say it can be modeled with a continuous growth. And then when you model it with continuous growth, then the formula happens to have an E show up naturally in it. We're also going to look at investments, compound interest. And compound interest, the way that it works is if something is compounded monthly, say you have $1,000 invested and you're going to be given 10% a year, which is a really high interest rate, okay? Current interest rates, if we used a current banking interest rates, they would give you decimal 0.0000000 interest per year. No, like basically banks don't give you any interest on your account per year. Maybe when you're a student so that you feel like, oh, I should keep my money in the bank. But once you get older, then they take all your interest really away. But let's say you got 10%. 10% of 1,000 is $100, okay? When something is compounded monthly, that means that after 1 month, they'll give you your interest. But they're not going to give you all 100 because 100 is what you would get in a whole year. They're going to take that 100 and say after 1 month, that's 1/12 of the year, so here's $8.33. And they put it in your bank account. And so you had $1,000, but at the end of the month, you now have $1,000.08.33. And you're all happy because you've got a little bit more money. At the end of the second month, they say, hey, you're getting 10% interest per year. You have $1,008 now and 33 cents. 10% of that is $100.83. So at the first month, it was just $100 is what you would make in a year. Now you've got $100 and an extra 83 cents. So they say, we owe you 1/12 of that now. So they give you another $8.33 plus 1/12 of 83, which is about 7 cents more. But now you get another $8.33 plus 7 cents more, so they add $8.40 to your bank account. And you now have $1,016 and some cents. And at the end of the month, they say, you get 10%, so that's $1,116, or $101 and whatever it is at this point. And they'll give you 1/12 of that. And so the way that compound interest works is you're not only getting your interest that you should get on your $1,000, which is $100 per year, and they're breaking that up into 12 equal months. But each month after that, you also make interest on the interest. And so your investment can grow faster with compound interest. And I just gave the example of compound interest per month. But if a bank would pay you interest continuously, every second, more than every second, every millisecond, they give you the tiny little bit that they owe you, then the number E appears. So it's another application of where the number E comes up. So with that in mind, we've got our parent graph of e to the x. We're also going to now have questions that can have transformations where E is there. So if I got you to graph this, y equals 3e to the x minus 2 plus 5, you would have to say, hey, this is my parent graph. Those are my 2 points, and that's my asymptote. Maybe I want to take out my highlighter and say the x and the e are the things that aren't going to be in my transformations, and then work from left to right. So if I took those 2 points, 0, 1, and 1, e, and my asymptote, y equals 0, and I went from left to right, the first arrows is all of your stretches and compressions. Can you see that you only have one stretch? And that is multiplying your y value by 3. So we have 0, 3, and 1, 3e. Or you can just 3, if that works better for you. And for translations, we do have two translations. That minus 2 is 2 to the right, and that plus 5 is 5 up. So we're going to have 2 to the right is easy. That's 2. 5 up is 8. 2 to the right makes this at 3. 5 up, oh. Well, you just write it as 3 plus 5. That's all you have to do. What about our asymptote? The only way an asymptote is going to change is if you shift it up or down. Do we do that? Yes, we do. So our new asymptote is at y equals 5. So they're a little bit messier because you're kind of dealing with a variable. You're keeping that e in there. And then when you go to graph it, it's a little bit messier just because 2, 8, easy to label, no problem. 3, 3e plus 5, a little bit harder to label. I should also 1, 2, 3, 4, 5 put in my asymptote, y equals 5. Where is 3, 3e, 5 going to be approximately? Well, e is 2.7. So 3 times 2.7 is approximately 8.1. 8.1 plus 5 is a 13.1. You might have your calculator to do those, but other than that, you're just going to have to estimate. And you label it as 3, 3e plus 5. As long as you have the shape of the exponential function correct, you'll be fine. So it's not any different than using nice numbers. It's just fancier when you use fancy numbers. But if you've never seen questions with a base of e, it can be very scary. But I wanted to show you it is the same idea, just with fancy numbers instead of regular numbers. Okay, so have a try at number 10.